My name is Vidhya, and I'm here to talk about a popular search relevance problem. As a mother, when I'm searching for a baby lotion, I get to see women body lotion with baby oil. When I'm searching for books, I get to see dinner tables. Sounds familiar? Yes, these are the kind of challenges the users of an e-commerce search are facing today. Let's try to understand a bit more about what our users are really searching for at target.com. Size small, animal print t-shirt, between $10 to $20. Or even for that matter, queries with gender, price, color, print, material, whatnot, to name a few. So dissecting and understanding these entities of a given query, as we call them, is quintessential not only to give the most relevant results to your user, but also this information would be useful for downstream models like ranking, facet discovery, and even related searches for that matter. And of course, to help your users find products faster without having to rewrite queries or without having to play around with facets. And of course, end of the day, you would want a better search conversion with contributing to your top line. So let's get into the solution part of it on what we tried out, the different approaches we tried to understand entities in our query at target.com. So we used an open source library to tag parts of speech of queries from our query logs, and hence trying to understand the named entity from there. Which also means from this exercise, we mined lexical patterns, and we built regular expressions to handle them. So this worked well for queries which had a grammar to it. Cool then. But then the second approach is the core topic for today's talk, is about the neural net-based approach which we took to understand our queries and entities better. But why? Obvious reasons were there are a lot of queries which we saw which did not have a grammar attached to it, or the queries had ambiguous signals, where in this case, red is not really a color. Or for that matter, there are incontiguous or missing out information from entities in the query. So my colleague, Vijayender, is going to deep dive into the second approach that we took.
Thank you, Vidhya. Yep. So we had a brief introduction, and also we observed a heuristics-based approach for tackling entities, and that definitely works well for simple attributes like price and age, primarily for the reason that these attributes, their expression hasn't changed even in the e-commerce. But attempting any such methodology for the other entities which we commonly see in the e-commerce would be a difficult task. And with that, we get into an NN-based model. And then the moment we talk about an NN-based model, the most important question is, where do we get the training data? So even if we look at other popular text analysis tools like Core NLP or Spacey, these are based upon statistic or neural net models, which tag pause NER in the common spoken English language. They have a pretty good advantage of training data, and these training data, like the pen tree bank, etc., these are human labeled, either human labeled or they're created from a semi-automatic process. This is an advantage for them, and this exactly is a disadvantage for the e-commerce queries. Now, we don't have an advantage of such training data, but on the other hand, we do have a good amount of query logs. We could mine patterns from we could mine entities from the query logs itself. So in our model, one of the things we want to bring attention to is that how we can extract training data for entity extraction from the click logs. And beyond that, we have a couple other things which we use in our model. One is the word-to-vec representation. This is to tackle the problem of sparsity. With respect to word-to-vec representation, what we have gone ahead is, rather than using the globally available word embeddings, either the GLOW or word-to-vec, instead of them, we have went ahead and pre-trained the word embeddings using the catalog corpus. And what we noticed is that using the catalog corpus and the pre-trained embeddings from the corpus perform better than using the generic embeddings which are available outside. I'll kind of give my understanding of why such thing was there. And beyond that, so in our model, we just, so given the queries, we vectorize them using the word-to-vec. And on top of that, we pass it through a bidirectional LSTM, which gives us hidden states at every time step. That is like, so let's take a query, blue shoes for kids. So blue shoes for kids is a variable length query. So the e-commerce queries are typically of variable length. Blue shoes for kids is of a different size as opposed to red DVD. And to enable learning on different sizes, we have gone ahead with using an RNN and the popular option being by LSTM. Apart from this, we have designed something called as an augmentation vector. This is to provide a lexical support to the model based upon the information which is already available in the catalog. So I'll kind of get into the details of a few of these things. The first thing being the training data extraction. So typically we have a good amount of clickstream data in e-commerce. So we have, by clickstream data, I mean we have a query which a user has performed and the corresponding documents they have clicked. Along with that, we have a rich catalog. In the catalog, the documents have attributes against them. The primary reason the attributes were developed, were actually populated is for faceting. Now we want to use this particular information and transfer the understanding from the facets back to the query. So we mix the clickstream data and the catalog and generate in tags of entities in the query. I'll just run through an example of to explain that particular one. So let's say a query is performed by a user Under Armour red shoes. Now what mostly users would do is, out of the results that have been provided, they would go ahead and click products which belong to the brand Under Armour, and similarly, they would go ahead and click products which belong to the, which are of red in color. So given a query and the corresponding clicks, now we can intersect the facets of the click documents and generate tags back for the query. So that is our training data. And so with that, we know that the Under Armour red shoes, Under Armour represents brand and red represents a color. So that's about the training data. And then the augmentation vector. This is one interesting thing which we attempted. So let's say there's a query. How would a human look for understanding what are the entities in it? If he knows what the query means, he would say that, okay, this portion of it is a brand, and this portion of it is probably a color. But let's say it's a completely new query. What user would be doing is, he would refer to the various dictionaries. Like a human being, what he would do is he would refer to the various dictionaries. He would look, okay, is this phrase found in a brand dictionary? Similarly, is this phrase found in a color dictionary? So as part of the augmentation vector, what we attempted is that we would encode the results of looking up in various dictionaries and provide it back as a sequence so that the model can understand it. There are two things that we devised as part of the augmentation vector. One is a dictionary, and then second is a scoring mechanism. Dictionary is just a dictionary. So in this particular case, it's a dictionary of all the brands that are available. And the second thing is a scoring mechanism. The scoring mechanism comes up with a numerical value for any phrase that is provided, and the value represents the likelihood of the phrase being present in a brand versus the likelihood of the phrase being present in the corpus in general. So we have a dictionary, we have a way to compute the scores. How do we supplement it to the model? We have seen that the query is of variable length. So what we thought is, we will take all the phrases in the query, look it up in the dictionaries, compute the scores, and then provide them along with the query. So let me give an example. Let's say we have a 4-token query, A, B, C, D. We perform unigram searches in the dictionaries and compute the scores. And that forms the first row of data. And then we perform the bigram searches. So we are looking up A, B, B, C, C, D, and so on. Similarly, we extend it to the trigrams. So with this, we are performing some sort of naive tagging and providing it back to the model along with the query. And because this is sequential once again, it fits well with the original input, which is the query, which is sequential in nature. I'll skip this. So this is the full pipeline. So what's happening here is we have a query. We vectorize the query, which is a sequence of tokens, into using the word2vec and then the augmentation vector. We then pump it into a bidirectional LSTM engine. That gives us with probabilities for each of the entities which are interested in. And on a similar front, we have the clickstream data. We perform a training data extraction from the using the catalog. We generate tag probabilities. We have the probabilities which we understand from the clickstream data and the ones which are generated by the model. We compute the a distance between them which stands as a loss. The common choices of distance are softmax cross entropy, or then we also attempted CRF, and backpropagation happens based upon this particular distance, and thus the model gets refined. I'll kind of once again go through this picture, go through this architecture in a slightly different manner. So it's the same information, but this time we are looking only at the vectors. So here's a 4-word query. Let's say word 1, word 2, word 3, and word 4. We convert the tokens in the query into embedding vectors. This is just the lookup of the words in the embedding dictionary. Along with that, we provide an augmentation vector, which provides the catalog information. So like I have said earlier, we encode the unigram matches, the results of the unigram matches, the bigram matches, and trigram, and so on. Now we concat both these information and then feed them into a bidirectional LSTM. The bidirectional LSTM actually gives us a hidden state at every time step. So there's one hidden state which is emitted when it looks at word 1, then a state when it looks at word 2, word 3, and word 4. These hidden states are once again processed through a fully connected layer and a softmax, which finally gives us the probabilities. So this is how the probabilities will look like. Given word 1, what is the probability of it being a brand? Similarly, what's the probability of the word 1 being a color and other, and so on and so forth. And in fact, if we observe even from the training data, we get a similar thing. Given word 1, from the training data, we know whether it's a brand, color, or other, and that's where we could try to bring this particular representation. We could try to train the model so that this particular representation gets as close as possible to the training data. Okay, with that, I'll come to a few model variations which we have tried and some results and like how the results of this particular model are appearing. So one of the model variations which we attempted is, what's the word embedding that we have to use? The popular options are GLOVE or word2vec, which are pre-trained. These are pre-trained either on the entire Wikipedia corpus or Google News corpus, etc. So we attempted with the embedding vectors which are available globally, and then we also attempted trying to build our pre-train the word embeddings on our own catalog corpus. What we noticed is that we get a slight edge, a decrease in error rate when we use the word embeddings that are trained on our catalog corpus. The kind of the way we try to digest this particular information is that when we build word embeddings on our own internal corpus, they try to capture a sense which might be specific for e-commerce as opposed to using a glove vector which is globally available, which has more generalization. So kind of, for example, as seen on TV is one particular phrase which represents a brand. Whereas when we look at glove vectors, it would have seen fewer examples of as seen on TV as a brand. And that's the understanding what we have got from, or that's how we are trying to interpret. Sorry? Yes. So what we try to experiment is that like we have taken, so are these ever switching if we take different samples of the data? And is the variance, let's say we take an exact same sample and run different training sessions, like with different initializations, what's the variance? Improvement is minuscule, I would say, from this to this, but there existed a particular difference, which always was in this particular format. And interestingly, the other interesting thing is we found that this difference was stark when we were attempting a item type classification using a model which is somewhat similar. And this is a chart where we are looking at the loss with and without the augmentation vector. We see a small difference in terms of when we provide the augmentation vector, the model slightly learns better. One other thought process is that instead of augmentation vector, if we could enable co-training of these words, the learnings would be similar. Here are the results. Here's a confusion matrix in a sort of sense. What we are trying to show is, given a word which is labeled as other, what percentage of it is also predicted as other, and so on and so forth. We do notice that, for the class called other, we have got the highest accuracy, naturally, because those are the words which are mostly present. And then for brand and color, slightly lesser, which made us curious as to, these are okay numbers, not something too great, but please notice the fact that this is against click-based tags. The labels which we have taken are noisy. So when we take the same data and go ahead for a human judgment as to how accurate the brand predictions are, in those places we have observed that for a small test set, like 1,000 queries, what we observe is like we have some 95% accuracy in terms of the brand getting tagged appropriately. Okay, here are some of the outputs from the model, the way it has predicted the various tags as. So we have tried to group the results into various sections. So here we see that long sequences are tagged properly. As seen on TV, active knee brace, as seen on TV is considered as a brand. Similarly, Five Nights at Freddy's, it's properly tagged as a brand. Here are a few examples of disambiguation. So red DVD, we could easily misunderstand red as a color, but typically red is a movie, so red is disambiguated well as a other token. Similarly, we see that in a query called Bluebell ice cream, Bluebell is treated as a brand. However, there's one interesting example which I want to quote over here. So we performed a search for blue bell-bottom jeans. So blue bell-bottom jeans, Bluebell is not detected as a brand, and blue is considered as a color. But yes, again, that's one of the example which we were keen on. And then we can see that there's a disambiguation between green tea and green bag. So green is a color in only one of the sense. and brown shoes and brown sugar. Similarly, brown is a color in only one of these hands. Also, the other thing which we're interested of this model is whether it could detect the various variations of the brands. So Melissa and Doug Peg Puzzle, or Melissa, Doug, Doug, Melissa, these were some of the things which could be tagged properly. And I would say that's primarily because when we have the click data, we know that the user, so we can relax the way we would match. Sorry, sorry. So when a user has performed a search and clicked a document, so when we are trying to figure out which portions of the query belong to which particular entity, we could relax the way we match. We don't have to go for an exact phrase match. We could go for token-based match. Because of that, we can detect the various variations, and that's one of the things which we were interested, and it comes through. Yeah, that's about it. Thank you, guys.